Today, I want to talk about CMOS technology and the CMOS inverter. CMOS stands for complementary metal oxide semiconductor. And recall that the MOS in CMOS stands for metal oxide semiconductor, which refers to the structure of the MOSFET transistor. And the C in CMOS means complementary. And that means that we use both N-channel MOSFETs and P-channel MOSFETs. So let's start by understanding how the CMOS inverter works. The CMOS inverter is composed of a P-channel transistor and an N-channel transistor. The P-channel transistor is connected to a power supply. Let's call it 2 volts. And the drain of the PMOS transistor connects to a drain of an NMOS transistor, and the source of the NMOS connects to ground, and the gate of the NMOS connects to the gate of the PMOS. So if we call this Vin for the voltage at the gates of the MOSFET transistors, we call the drain voltage V out. So let's review. This is the P channel, and this is the N channel. Recall from the previous 2 videos that the P channel and N channel operate in a similar fashion, except the voltage polarities, the E fields, are reversed. And for completeness, I might include the 4th terminal, which is the well connection for the PMOS, and connect that up to the high voltage. And the substrate connection for the NMOS will connect that down to ground. Now recall that this is the source voltage, this is the gate of the PMOS, this is the drain of the PMOS, this is the drain of the NMOS. This is the source of the NMOS, and this is the gate of the NMOS. So let's consider how this inverter operates. How do these transistors work together? Let's start by plotting a DC transfer curve. Let's plot the V out versus V in, where this is the V in voltage, this is the V out voltage. And let's start with V in at 0 volts at this point in the origin. Let me change colors. If we have 0 volts at the input, we have a strong E field. The source is sitting up at 2 volts, so we have a strong E field in this gate region, and we form a channel in this PMOS transistor, and our NMOS transistor is in the off condition because the gate voltage is below the threshold voltage that turns on the NMOS transistor. So in that case, since the P channel is on and we have a resistor that connects the V out up to the 2 volt power supply, so the output voltage is sitting here at 2 volts. And as we increase the input voltage, the output voltage stays the same until the N channel starts conducting. When we reach the threshold voltage, Vt of the N channel, we start conducting. This curve looks something like this. At this point, where input voltage is perhaps around 1 volt, and both transistors are conducting now. Then as we raise the input voltage higher, the N channel conducts better and the P channel conducts less. And eventually the output goes to 0 and the input goes to 2 volts. So this is called the DC transfer curve. And it's a plot of the V in versus V out. And the significant thing is that in this part of the curve, we're drawing essentially no power dissipation. And in this part of the curve, there's no power dissipation because both transistors are off. Now, when both transistors are on for a brief time, when things are switching, we get a current. If I plot the drain current, I'll get a spike of current, something like this, where this is the I drain, or the current flowing in this branch, I drain. So the beauty of the CMOS inverter and CMOS in general is that when the transistors are just sitting there, where say the output is at a high voltage or the output is at a low voltage, in both cases the power dissipation is almost nothing. So we could have a lot of inverters and similar circuits on a CMOS integrated circuit and the power would be quite low. The chip wouldn't heat up that much. And that's a big, big plus when you combine a lot of transistors together to do different functions. And that's the beauty of CMOS, is that you can combine a lot of functions together and not dissipate much energy. So let's talk about the CMOS inverter in more detail. Let's draw the symbol for this CMOS inverter. The symbol for the inverter is this. It has an input that I'll call V in and an output that I'll call V out. And this little bubble means that an inversion takes place. Now what that means is if I put a low voltage on the input, for example, if I put 0 volts here, I get a high voltage at the output. I get 2 volts at the output. So it has inverted the input. Whatever is at the input gets inverted. Now if I have a high voltage or 2 volts at the input, I turn on the N channel, I turn off the P channel, I get 0 volts at the output. So what can you do with an inverter? What is it good for? Let's take an example. What if I connect up 2 inverters together? I'll connect this output of an inverter to the input of a different inverter. I'll connect this output back to this input. So what does this circuit do? Well, let's analyze it. Let's presume that I have a low voltage here. I have 0 volts. Now this top inverter is going to take the 0 volts and it's going to invert it. In our example, with a 2-volt power supply, it'll invert it to 2 volts. Now the inverter at the bottom will take the 2 volts and it'll invert it to 0 volts. And so this pair of inverters is in a stable state. But let's say that I do something and I force this voltage to 2 volts. So it's no longer at 0 volts. I'm going to force it to 2 volts. This top inverter will cause the output to be 0 volts. And 0 volts at the bottom inverter will cause the output to be 2 volts. So everything is compatible. So these 2 inverters form a memory. It can remember data. Once this voltage is set, or this voltage is set, it will remember the information. So I can use these two inverters in a memory circuit. And later, in a later video, when we discuss the RAM cell, you'll see these two inverters with a few additional transistors here and here to allow data to come in and out of this inverter pair. So we'll talk more about that in the future, but I just want to introduce what the inverters can do. Let's consider what else we could do with an inverter. Let's say that we take some inverters and we'll connect one inverter to another inverter. We'll connect this to another inverter. And then we'll connect this output back to even more inverters and to another inverter. And this inverter output will go back to this input. So what does this circuit do? Well, let's analyze it. Let's assume that this voltage here is 0 volts. In that case, this inverter output will be 2 volts. This will be 0 volts. This will be 2 volts. This will be 0 volts. And this will be 2 volts. So we have a contradiction. This output wants to be 2 volts, but we started out with 0 volts. So what happens is that this output will switch the original 0 volts, it'll switch it up to 2 volts, and now things will change. This will go to 0 volts, this will go to 2 volts, 0 volts, and so on. It's called a ring oscillator. And if we examine the voltage at any node in here, let's take this node, and we examine that voltage versus time. So if this is our time axis, and if we initially start out with 0 volts, let me change colors. If we initially start out with 0 volts at that node, and after 5 inverter delays, it's going to switch to a 1. And then that 1 will propagate through 5 inverters, and in a later time, the output will switch back to 0. Then that 0 will propagate through 5 inverters, and the output will switch to a 1. And so on and so on. And again, this is called a ring oscillator. And as long as you have an odd number of inverters, this thing will oscillate. If I were to add another inverter in here, it would become stable. It wouldn't oscillate anymore. But as long as I have an odd number of inverters, I'll get the square wave output. Now, if I add more inverters, instead of 5 inverters, say I add 11 inverters, the delay times will get longer. It'll do something like this. So this circuit can produce a pulse, but not a very accurate pulse because it's very sensitive to power supply conditions and process variation. But nevertheless, it can create an oscillating function. So hopefully this gives you some idea of the basic CMOS technology and why the CMOS technology is low power dissipation and some of the things you can do with an inverter.